All right. So I am going to um, do a completion of the lecture from this morning, and um, it shouldn't take too long. There's only a couple of slides to go through, but if you haven't watched the lecture up to this point, then this probably won't make a lot of sense. So feel free to check that out first. Um, it'll be available here and on YouTube at some point. So this was I presented this morning, and now it's just afternoon, and I'm going to finish up. The discussion is about distributed consensus, and what I left off at was I was talking just had finished talking about quorum consensus, and then I went to discuss this interesting work that was done in the 90s around what they called crumbling walls. And so the picture is actually lifted directly from the paper. And in the paper, their point is, and this is what's actually really interesting about this, is that they organize the nodes in their system um, into rows. And what they observe, and this is a much more theoretical paper. They actually have a formal proof model for proving the properties of what they're discussing. So what they said was, we're going to organize our rows, our nodes into rows, and then in order for us to have a viable consensus, we must have every single node in a row be consistent. In other words, voting for whatever the quorum value is. And then we need to have at least one element in each row, or I'm sorry, one element in each column that's present in the row that we've captured that that are in other rows. So the point is that what you need is, think of this as, we've achieved consensus in this one. I mentally, I think of this as data centers. We've achieved consensus in one of the data centers. One of the data centers says, and that's a row, one of the data centers says all of the servers in this data center have in fact actually captured uh, the information that we need here. And then we have at least one node in the other data centers that represent elements of the column that also are um, are present. And I'm looking at this picture and going, how does that work with the fourth column? But it's a picture, and so it's just trying to demonstrate the basic point here. I'm not sure if the picture is the issue or if I'm missing something. Um, I'm not missing the takeaway from the paper. The paper is interesting, and they do a very good job of laying out the formalism here. The reason they call it a crumbling wall is you'll notice the rows do not have to actually be the same size. So and there are other things. I actually didn't mention this in the lecture earlier today, and I really should have, and that is that one of the important aspects of all of these quorum consensus models is that we have this implicit assumption that we have non-correlated failures. And in the real world, we find that there are often correlations in our failures, and that will make our solutions a lot less robust, a lot more vulnerable. And so I haven't talked about that at this point. I probably should talk about it at some point in the future, and that is, what do we deal with? How do we deal with correlated failures? Because correlated failures are real world, interesting, challenging problems, and they will challenge us. So, at any rate, one of the things to notice is that crumbling walls essentially becomes a generalization of earlier quorum-based solutions. So you can, in fact, take Gifford and reader-writer quorum-based, and you can model it into this kind of a system if you want. So this is a generalization of that model. Let's look at, I'm not going to go into great detail. If you want to know more about all of the nuances and details of the proof, for instance, you really can go look at the paper. What I did find interesting is that what this provides, and so what they're pitching is in fact what they call CW log, um, which is a crumbling walls log. and it has an optimal load with a small quorum and high availability. So we don't have a lot of overhead, the load being the overhead that's necessary for us to get to quorum. And what's really cool about this is that this actually provides you with a model that you could use under the right circumstances for constructing a quorum system that does not require a majority. I mean, the majority thing is pretty easy to see. This one's a lot harder to see, but on the flip side, it's a lot more interesting to think about and to say, how could I possibly use this? I have to admit, I haven't actually seen a system try to use this, and so there may be pragmatic issues around using it. I had somebody point this paper out to me a number of years ago, and it's always intrigued me because it is an interesting piece of work. All right, so lots of symbolism here, lots of symbols being used. So the load of the CW log system is proportional to 1 over log n, where n is the total number of nodes. So availability then in this system is proportional to um, this number, so n, the number of nodes, to the negative of this value epsilon, and epsilon in this case is is the probability that something's going to go wrong. So the interesting point here, and this is really about dealing with the failure case, our availability is related to what we think might break. So the more things that we think are going to go wrong or have a high probability of going wrong, then the more likely it is that we're going to compromise our availability unless we have more robustness in the system. And so one thing we can do to make that better, obviously, is we can use larger numbers of nodes. So we can increase n. The really cool thing about this was they actually said in the paper, and it blows my mind because this is literally this very formal logic paper, and what they actually said is that in their analysis, the probability of any individual component failing needs to be less than 0.432. And you're like, okay, so less than 0.4%, basically. And and that number is there because they basically say that in order to guarantee reasonable availability, you need to have this relatively low likelihood that something is going to fail. And they take a simplified model here. They basically say that that needs to be the probability that any individual component is going to fail. But it's not too hard to step back from that and say, as long as the worst component has a probability of less than um, uh, actually it's 4.32% probability of failing, then you can use this reasoning, and that doesn't feel too bad to me. I mean, what is, of course, that's going to depend on what your time scale is. If your time scale is 24 hours, is there less than a 4.3% chance that something is going to fail in the next 24 hours? And if yeah, our components are generally pretty robust, and that's why this work is interesting to me, because we know that we're probably not going to have, I mean, I think of like disk drives, and in disk drives, we have failures that are usually measured in numbers of hours between mean time to failure is the usual number that we use with like storage devices. Again, we're assuming uncorrelated failure. If I use, and I've mentioned this example before, but here's where that starts to make a difference, because if I have correlated failure, then that probability gets skewed very quickly because I can't actually think of this as the probability that any one component, independent of the others, is going to fail. Because now all of a sudden it means the probability of multiple components failing is actually much higher than if they were truly decoupled and independent of each other. So in other words, if I go out and I buy myself a bunch of Samsung 980 Pro SSDs, NVMe SSDs, 2 terabyte apparently. There's actually a current issue with them where they go into there's a bug in the firmware where they think that they've exhausted their write capability, and it literally bricks the device, and the only thing you can do at that point is RMA it and get it replaced. And I happen to have that drive in my computer, so I've been watching that. I need to watch and see what the outcome of that is. But the point here is that if I have a bunch of those because I got a good deal on them, then there's a problem. And this is an interesting thing you have to think about when you build real world distributed systems, as opposed to, we're still kind of talking about this from a theoretical model. But when we get into the real world, where we're actually building with real hardware, our purchasing people are going to undermine our ability to build heterogeneous systems, because they're going to want to save as much money as possible. And so they're going to say, well, we need 1,000,000 of these things, or 1,000 of them, or 100,000 of them, or whatever it is. And they put it out to bid. And what they're going to end up getting is exactly the same thing from probably the same batches. And we know from prior experience, have high correlation failures. If you want to avoid those kinds of failures and you want to get that kind of independence, you actually need to force people to do things that are expensive. This is a theme in distributed systems. So, for example, if I'm going to build redundant drives, and redundant drives are a great example of where you can use this kind of crumbling walls model, for instance. Um, I need to use devices that have different characteristics, and thus try to minimize the likelihood that they have correlated failures. So I'm not going to use a Samsung 990, or I'll use a Samsung 980 and a Samsung 990. They're made in different factories. They might be by the same manufacturers. I don't have complete heterogeneity. And then I'll use a Western Digital driver. Maybe I'll use Western Digital and Samsung and SanDisk and Crucial, and so I'll mix products that are from different vendors to try and get different to decorrelate those failures. Of course, I might be using the exact same motherboard to talk to them, and so there still is some potential for their failures to end up being correlated, because there's a bug in the motherboard. Um, but at that point, you can argue that that's not a failure of the NVMe device; it's a failure of the firmware, or the hardware on the motherboard. And what can I do? So I can split those out and I can put them on different controllers. Well, now I have the same PCI bus. And so I split them and I put them in different computers. And remember, that is part of this analysis. One of the benefits of us starting to split things and put them into different computers in a single data center is I can have different racks, I can use different motherboards, I can use different devices, I can use different power supplies, I can use different networking equipment, and that way I can start to spread out those correlated failures. But from a modeling perspective, from the design perspective, and from the algorithm perspective, we are going to assume that you're going to do that actual work to eliminate as much as possible those correlated failures. So there you go. So now we have an actual model. The crumbling walls thing is because we don't need to have the same number of elements in any given row. And the model here then is that we have enough state, enough information for us to reconstruct that data across all of the nodes that have it, because um, we have copies that will allow us to do that. Like I said, I'm not convinced that picture is right, actually, which I think is kind of interesting, but I'll leave that as an exercise to the reader for now. Okay, so the challenges do remain, and the key here is to keep in mind that we have kind of been implicitly assuming that there's some sort of a coordinator for this activity. In Gifford's work, there was an underlying assumption that we have a transactional system that allows us to do consistent updates across our replicas. We are going to be able to weaken that, because so our definition of consistency remains the same. What we get to weaken it is because we can start working forwards as soon as we have a quorum. So we don't have to have complete saturation of all the copies of it. We can just simply know that there's enough copies of it out there that our consensus algorithm will allow us to confirm, and no one else will be able to get the wrong value. Like thinking crumbling walls, since I have one entire row Um, I can't get the wrong value in the rest of the state because there's always someone else who has the right value. Because remember, even if I take that row out, then the columns will be able to fill that in, and that's why I'm questioning that picture. So, okay, so we have some ways of doing this. We haven't really talked about how we're going to do that yet. We did have in Project 3, we kind of had this coordinator, but the coordinator here wasn't for database coordination. In Project 3, our database coordination really was a primary replica model where or chain replication, if you want to think of it that way. It's not. See, in chain replication, we would have read from the backup. In the primary backup model here, we always read from the primary. The backup is really just there in case of failover. So if we have our view server, what it's doing, it's not arbitrating the consistency of the database. It is actually providing the consistency of defining um, who is the primary. And I walked through this earlier in class. I have a view server, a primary, a backup. There are only three ways that I can uh, partition this network. And we walked through those earlier. So I'm not going to walk through it again. If you're interested in that, it's in the lecture from this morning. The point is because there are three different nodes that get to participate there, we have partition resistance. We are not going to end up with two partitions that both think that they are in charge. We have weakened our consistency a little bit here because we don't want clients to constantly pinging the view server, but we've kept the window there pretty small because the client is going to periodically refresh its configuration state. And once it notices that the view server is not available, then the client is going to stop talking. The client's going to go, I don't know who to talk to because I can't talk to the view server. That means that they are um, uh, if the view server is the one that gets partitioned off, so the view server is the only one that can't talk to the world because somebody had disconnected the network cable, the clients will start to lose access. And so that's not a great answer for our availability story. And we are going to have to do better than that. But here's the interesting thing. That's just a database. It's a database with a tiny little bit of state. After class today, I was talking this through with one of the students, and I was pointing out that what we are in essence doing is we are layering our problem space. So when we have a database that we need to keep in constant replication, then we'll have like the primary backup model where the primary gets the backup to be consistent with the primary, and then client comes in, asks the primary to read. The primary doesn't need to talk to backup to answer that, just answers it. So it's very fast for read. Then the client comes in and asks the primary to write. So the primary writes to the backup so that if things crash, then the backup will be consistent with the primary. Now the primary answers, and then the primary returns back to the client. Now you can see that there's some interesting questions around what does the client do if the primary goes down while it has an outstanding request? And the answer is it's basically going to have to repeat the request. And so it's going to repeat the request. It's going to find out that the operation has already been done. Um, and I'm going to hand wave here a little bit because this isn't really AMO so much as it is the client has to know, hey, the view changed, so I have to try this operation again. And the first thing I'm going to have to do to recover is I'm going to have to say, yo, primary, what's the value of this key? And the primary is going to say there's no key, or here's the value of this key. And if there's no key, or if the value is different than what the client thought it should be, then the client can retry it. They can do another put on the key. when we start talking about a configuration database, it's actually very small. It's not a large database, or if it is large, then the configuration data that it has is completely decorrelated. Well, hopefully decorrelated. So in other words, if I'm in project 3, the amount of state that's in the view server is tiny, and we are actually using a consensus quorum mechanism for allowing the view server to change. And we've defined very specific semantics there. So the view server comes up, picks a server, and says, you are now the primary. And then the primary acknowledges that view. So the primary says, I accept the role of primary. Then the view server says, okay, and I'm going to pick a replacement for you. So we're going to have an understudy, and the understudy is going to be the backup. And then that view server proposes that, and the only entity it can propose it to is the primary. And the reason for that, of course, is that the primary has a different consistency protocol that it has to run in order to ensure that that backup server is in sync with the primary. The view server is not involved in that process. The view server doesn't actually know. The way that the primary tells the view server that it's okay to update the configuration is the primary acknowledges the view. So now when the primary acknowledges the view, guess what? We have two of the nodes agreeing on what the state of the system is. And that's all we need to move forward. We can recover from that. If one of the servers drops off, we can handle that. And when you're working on your project 3, that would be clearly what you should be thinking about. What do I do in these various cases where the view server is partitioned off, the primary is partitioned off, the backup is partitioned off? Well, so when do we actually turn this into a replicated database? Because you'll notice the view server isn't replicated. That is the one thing that we haven't replicated here, and it says that in documentation. It says, well, we don't really have this. So we could use this kind of replication work that we're doing to replicate this configuration information. And now when a client comes up, it could talk to a view server that was replicated. Examples of this include Zookeeper, which is an Apache project that is used for replicated state, and it implements the Paxos protocol, which we're going to be talking about next week. And we also have etcd, which uses the RAF protocol, which is also known as view stamp replication, and we'll be talking about that next week as well. So these are our configuration databases. This is what people actually use them for. We pay the high cost associated with getting the strong consistency guarantees that we can get out of Paxos and Raft in a lossy environment so that we can guarantee high availability, because these are infrequently mutating states. We don't get a lot of change. You don't really want to run Paxos or Raft, to be honest, in a general purpose database where lots and lots and lots of things are changing. Of course, having said that, Project 5 is going to be a sharded key value store using Paxos. And we're going to be talking about some of the motivation for that, because we're taking a really heavy tool set, a very specific kind of quorum replication, and implementing that in a very general purpose database. And there's a reason for that. And it turns out that that reason is in fact exactly why Amazon ended up building Dynamo, because they needed consistency. Now they accepted eventual consistency, but they needed consistency and high availability. So our coordinator eventually needs to be highly available as well. And it turns out that we can solve these problems together. In the primary backup model, even if I have multiple backups, I still have the primary effectively acts as the coordinator for the operations with the replicas. What we're going to want to do is we're going to want to break that dependence on a primary. So we are going to end up implementing a protocol that involves choosing the coordinator for a given transaction before we start the transaction. And there are lots of different ways we can do that. It is still an active area of research. Heidi Howard graduated with her PhD in 2019, and most of her research work into her PhD was in fact revisiting Paxos and Raft and looking at various trade-offs and assumptions in the earlier models and ways to improve their performance and their behavior by being flexible about some of the requirements. I might go into that in a little bit more detail later in the term, depending on how much time I have. It's not core, but it's still very interesting. So the question you should be asking yourself at this point is, how are we going to actually construct such a system? And I'm going to foreshadow this by pointing out this is a question I will be answering next week. So let's summarize the lesson. We talked about quorum replication. We reviewed our previous replication mechanisms, including primary primary backup replication, chain replication, crack. We talked about consistency, and I specifically framed that in terminology that we use in the CAP theorem. And then we talked about voting protocols, these quorum protocols, and how basically how they function and what we can do with them. Honestly, quorum protocols are actually still used very actively today. They are generally quite useful, generally easy to reason about. I'm not talking about CW log, where I think that one's going to require a lot more wrapping your head around. It would be interesting to look and see if anybody's actually implemented a general package for doing that, because it could be a very interesting kind of project that I might suggest in the future for other classes. So since this is being done after the class, I'll save any questions for either Discord or online or later. So with that, I'll wrap it up. I hope you've enjoyed this lecture, and I will talk to you next week when we dive into Paxos. Have a good one.